Okay, hi everyone, Mr. Ang here. So these are the answers to the milestone quiz that I handed out in class. Okay, so question 1. The following figures show a force exerted on a pivot at different angles, and we are to construct the perpendicular distance from the pivot to the line of action of each force. Okay, so what is the perpendicular distance? Okay, you might recall the perpendicular distance must be number 1, perpendicular, okay, to our force. So what that means is you have to have it at right angles to the force. Now, of course, it then has to go from the force to the pivot. So how you do that? Okay, of course, you don't just draw a perpendicular line randomly. What you actually do is perhaps you take a set square and then you slide it along the force like so until the other edge of it reaches the pivot. So there you see that this is the perpendicular distance. Okay, it's slightly off on my diagram there, but I'm sure you get the point. For question 2, the second force, the same thing applies. You just put a perpendicular line and then you slide it, slide your set square until the other end touches the pivot. Okay, so the pivot there has been marked out with X, so you just need to connect this to your force. Now, the third diagram, the third force, might be a little bit more confusing. Okay, why is that so? Because when you draw your perpendicular line, you might realize no matter how you slide it along your force, there is no way for you to connect it to the pivot. However, you have to remember that the perpendicular distance is from the line of action of the force, not just what you see in the diagram. And the line of action of the force extends beyond the actual arrow itself. So you can actually slide the set square, construct this line, and you will find that this is the perpendicular distance. Okay, these three questions, in fact, do not actually cover one of the other scenarios, which is perhaps you even need to extend your line of action further up and then draw a perpendicular distance this way to wherever your pivot is. So please remember that the line of action, you can construct a dotted line on either side of the force, and then you can slide your set square along it to get your perpendicular distance. Okay, and you must remember the perpendicular distance, so please show that it is actually at right angles between the line of action of the force to the line itself. Otherwise, this is where marks could potentially be lost. So now we move to question 2. Question 2 states that a light rod of length 3 meters is pivoted about one end as shown in the diagram below. Before we move forward, something very important to take note of is this word here, light. When you see the word light used to describe any object, what we mean is that this object has mass equals to 0 and therefore its weight is also 0. Okay, so our rod here is taken to have no weight, meaning that this diagram here, there is no force, due to the weight of the rod. Therefore, this diagram has all the forces that we are concerned about, the 50 newtons as well as this force F. Okay, so you can see over here, this 50 newton force acts downwards 1.2 meters away from our pivot, and we want to find the magnitude of the force F on the left over there required to balance the rod. So the first thing before we even start, is to realize that we are trying to balance the rod. So what we should apply is the principle of moments. And the principle of moments tells us that the clockwise moments is equal to the anti-clockwise moments. Now, given that, we have drawn a pivot, there on the right side if with the triangle over here. So this is our pivot here. We can take a look at the forces F and this 50 Newton force and decide, based on how it wants to rotate the rod about the pivot, whether it is providing a clockwise or an anti-clockwise moment. And I think it's going to be very clear, that you will see that the 50 Newton force is actually going to provide an anti-clockwise moment. It wants to rotate the rod this way, and that is anti-clockwise. While force F is going to provide a clockwise moment. And now these moments are balanced, And of course, we have the moment is equal to the force times the perpendicular distance. Now, both of these forces are vertical. Our rod is horizontal. So our perpendicular distance will be 1.2 meter for 50 newtons. And for force F, the whole length of the rod, which the question states is 3.0 meters. So from here, okay, we have clockwise moments equals to anti-clockwise moments and also our formula for the moment. So what we have here is clockwise moments, which is force F, whatever its magnitude, times the perpendicular distance of 3.0 meters, and then equals to the anti-clockwise moment, 50 newtons, times the perpendicular distance of 1.2 meters. Once you do the math, which I'm going to omit, okay, the force that you get is 20 newtons. So the important part to realize, okay, is that actually this section here is more important than getting to the final answer in terms of the marks. In order to demonstrate the understanding, okay, we would need to see you write down the statements on top. These statements actually justify how you are able to come to this equation over here. Okay, without the principle of moments, clockwise equals anti-clockwise, and the formula for the moments, what you get here is just an equation with no explanation. And in fact, okay, if we are going to be very strict about things, you wouldn't get any marks because this doesn't necessarily demonstrate the understanding. Of course, getting the math correct, okay, doing your multiplication, division, and whatever other mathematical operations in order to get the final answer of F equals 20 newtons is important as well. But generally speaking, more marks are going to be allocated to the correct usage of the principles or the laws rather than just the math itself. Okay, so please take note of this. And if you always are able to pause the video, okay, so if you need to pause or rewind the video, please remember to do so as well. So now we move on to our third question. The third question states that we've got an 8-meter rod of weight 300 newtons suspended by both ends, okay, from two ropes P and Q, and we've got a 500 Newton weight suspended 2 meters away from P. We want to calculate the tension in the ropes, but before we do that, let's make sure that our free body diagram is complete. So how do we do that? We know that tension, okay, is going to act along the two ropes. These ropes you can see are vertical, so we can actually just draw and say that there is a force, let's call it Fp, and a force, let's call it Fq, acting on either end of the rope. Okay, and additionally, it also says that it has a weight of 300 newtons. Now, the other thing is, where does this 300 newtons go? It's 8.0 meters long, and we know that the center of gravity should be in the middle. So let's just draw a weight here. W equals to 300 newtons. And in order to make sure, okay, that we do not get the perpendicular distances wrong, because of course, anytime we look at moments, there's the perpendicular distance. Let's also draw out our distance. It says 2.0 meters from P. That's where this weight is suspended. Okay, and as well as the fact that we are going to have the weight of the rod 300 meters. That would be 4 meters away from P and also 4 meters away from Q. Okay, so now that we've actually labeled our diagrams and drawn all our forces, we can now start to apply the physics. Again, same thing, the principle of moments, clockwise equals to anti-clockwise. We also need the formula for the moment, force times perpendicular distance. Now, the important thing in this question is to realize that we have two potential pivots. Okay, there is no natural pivot unlike the previous question. You could either pick Q as the pivot or P as the pivot. In fact, if you wanted to, you could pick this point here as the pivot or the center of gravity of the weight as the pivot. However, picking either of these points, okay, is not very helpful because then you're going to get one equation with Fp and Fq, two different unknowns, and it's probably going to be very hard to solve for them. So what we're going to do is to take one pivot in which either Fp or Fq does not have a moment. So we only have one unknown in it. So let's say we take the moments about P over here. Okay, so let me just mark that out to make it very, very clear. We take moments about this point, P, and then we need to find our clockwise moments and our anti-clockwise moments. So looking at this, we know that Fp does not have a moment because it is passing directly through P. It is not going to provide a turning effect. The 500 newtons, however, is going to provide a clockwise turning effect. The weight, 300 newtons, a clockwise turning effect. And Fq is going to provide a counterclockwise turning effect in the opposite direction. So with this three different forces, with three different moments, we are able to calculate the effective result. So moments about P, the turning effect of the 500 newtons is clockwise. So 500 newtons times 2 meters on the left-hand side. The weight, 300 newtons times 4 meters on the left-hand side as well. So we have these two terms here. And on the opposite side of the equation, because it is providing an anti-clockwise moment, we have Fq times 8 meters. Again, I've omitted the math to get our final answer of Fq equals to 275 newtons. It is important for you to do the math properly, but I'm here to mainly show you, okay, how we get to this equation using the logic, using the free body diagrams. Now, after this, what we need to do is to find Fp. You could actually repeat this whole process by using Q as the pivot. However, that is going to be very long drawn, and there is actually an easier method, okay? And what that easier method is to use Newton's first law. Because the rod is suspended, it is at rest, is at equilibrium. Our sum of upward forces and downward forces are going to be equal. So for upward forces, you see over here, Fp plus Fq, and our downward forces, 300 and 500 newtons. So these are going to be balanced. Therefore, again doing the math, Fp is going to end up with 525 newtons. Okay, if you would like, you can always pause this video, attempt to calculate the moments, taking the point Q as the pivot. Doing so to verify is also very good practice, and you should be able to get the answer 525 newtons for Fp. Okay, so if you'd like to do so, you can pause the video. If not, we are going to move on to the next question. So our next question states that a uniform box of height 50 cm and width 80 cm has a weight of 100 newtons and is resting on the floor. A horizontal force is exerted on the top corner of the box. By drawing a suitable diagram, calculate the minimum force required to rotate the box. Okay, so here we don't even have a diagram, and it's very important that we start by drawing it. Okay, the question even tells us to draw a diagram. So first, let's have a box. Okay, I'm not going to label the height and the width first because I think it's very obvious. Next, let's look at the forces. Okay, we have a weight of 100 newtons. Okay, so let's label this weight equals to 100 newtons. And then we have a horizontal force exerted on the top corner of the box. So this force here, we don't know what it is. Let's just label it F. And you will realize that we can use our principle of moments. Okay, clockwise equals to anti-clockwise moments because we want to be able to rotate the box. Now, again, the formula for moments. And we have to use a suitable pivot. So if you've got a force over here in this direction, okay, let's use this corner as the pivot, and we will see that that will cause the box to rotate this way. In a way, what we're doing is we are making the box stand up. So now, knowing that, we can find our perpendicular distance. Okay, with the corner of the box here, the perpendicular distance of the weight is going to be 40 centimeters because it is coming from the middle of the box. And the perpendicular distance of the force F, horizontal force F, is going to be 50 cm, which is the height of the box. So, knowing that, okay, we have the moments from this bottom corner, and we see that the weight has a certain turning effect, okay, and the force has the opposite turning effect, which I drew earlier. So, clockwise moments F times 50 cm. I've turned it to SI, converted to SI units, so F times 0.5 meters. And for the anti-clockwise moments of the weight, 100 newtons times 0.40 meters, converting it to SI units as well. This will give you the force of 80 newtons minimum required to rotate the box. Now, you might ask yourselves then, what if, okay, instead of drawing the force on that corner, the upper right corner, I draw a force pointing the opposite direction, or a force on the upper left corner pointing inwards? Now, you will notice at the same time, very nicely in this question, if this force indeed, okay, was drawn this way instead, okay, someone is instead of pulling from the right, they are pushing from the left, the perpendicular distance will still remain 50 centimeters to the pivot. Additionally, the force will still be the same, so equation will still be the same. And if you draw something like this, of course, you have to choose the pivot wisely. If you imagine this new diagram now, if we erase our pivot from this bottom right corner and we have a pivot here, what we are going to get is that this new diagram over here, you're not actually going to get any sort of rotation because both of the forces are going to result in a clockwise turning effect. Okay, so there's nothing here that will cause it to rotate about this pivot. You're going to be trying to rotate it into the ground, and that's not going to be possible. So now let's move on to question 5. Okay, question 5 states that we've got an irregular laminar. It's got a center of gravity C marked out, and it's suspended from point X. So the laminar is released and allowed to rotate freely, and we have to state and explain how it moves when it's released. So firstly, okay, what we have to do is first realize that the center of gravity is where the weight is going to be exerted from. Now, in this question, there are no calculations. We do not need to know, okay, what the magnitude of the weight is. Secondly, the pivot over here is very clearly marked out X. So we will realize that it has a very clear perpendicular distance over here. Now, when it is released, okay, what is actually going to happen is based on our understanding of real life, the laminar is going to rotate. And how is it going to rotate? It is going to rotate anti-clockwise. Why is that the case? Because the weight acting on C has a perpendicular distance, therefore there is an anti-clockwise moment about the pivot. So that is state and explain, 2 marks, quite straightforward, but the key concept is that there will be an anti-clockwise moment. Now for part 2, okay, after a while of being released, it comes to a rest. State and explain the final position of the laminar. Now, I don't have a fancy animation here to rotate my laminar, but the answer, as you might very well know, is that the laminar rotates until C is vertically below X. Why is that the case? It's because when you have your final shape, X and C, what you actually want is the weight, okay, to be directly underneath so that its line of action passes straight through the pivot. Because it's passing straight through the pivot, there's no moment. Alternatively, you could also say that the perpendicular distance is zero. Okay, so the perpendicular distance being zero means that there is no moment as well, and that's how the laminar comes to rest. Okay, so I hope this quick five questions have actually given you a better understanding of how to apply, okay, the principle of moments, the center of gravity, and all our calculations into solving such questions when it comes to the turning effect of forces. Okay, as always, the video is here going to be uploaded, so you can always pause it, repeat it, slow it down. Okay, if you need a little bit more time to re-watch it to understand the concept.